general, when we talk about Snell's law, we know that it is nothing but n1 sin theta 1 is equal to n2 sin theta 2. N1 and N2 are the refractive indices, and here we are actually representing this N1 and N2 as mu1 and mu2. Okay. So sin theta 1 is actually the angle that the incident ray makes with the normal, and theta 2 is the refracted ray, that angle it makes with the normal. So if we are considering an interface, and this is the rarer medium, this is the denser medium, and maybe this is the normal that we have. Okay. Usually what happens is that a ray of light will actually pass from the denser to the rarer medium, and then it will bend away from the normal. So this angle will be nothing but theta 1, and this particular angle will be theta 2. Okay. So this is something which you already know, and this is the refractive index of the first medium, and this is the refractive index of the second medium. Right. This is the law of reflection that we know, refraction. And from here we can just find out what is my sine of theta 2 by simply knowing what are the refractive indices. So maybe this is water and maybe this is air. So for air, you know the refractive indices is 1. So you just simply put mu2 as 1, and this will be just mu1 sine theta 1, and easily you know what will be the angle of refraction. Okay, that's very simple. Now, as we understood from the idea of total internal reflection, that it will be incident at a certain angle, let's say theta 1, and at that certain angle the ray won't be refracted, instead it will pass along the interface. That means this angle that is there will be 90 degrees. So that means theta 2 will be 90 degrees. So whenever we solve this particular problem, we have to remember mu1 sine of theta 1 is equal to mu2 sine of theta 2. Okay. We need to consider this relation, and here we can say that theta 2 and theta 1 are actually represented in the diagram. So in this case, okay, what we have here is theta 1 is here and theta 2 would be 90 degrees. So theta 2 is 90 degrees. Sine of 90 is 1. So if we just simplify the relation, we can just write it down as mu1 sine theta 1 is equal to mu2, or we can also find out what is sine theta 1. So that theta 1 is the critical angle. So I can simply find out what is sine of theta 1. And sine of theta 1 is nothing but mu2 by mu1. So you see, it depends on the refractive index of the two medium. And this theta 1 can be represented represent the critical angle, theta c. Okay. Now what happens is, if we go beyond, that means if we are increasing the angle to, let's say, this particular value, what is going to happen is the ray of light is not going to pass along the surface. The ray of light is also not going to get refracted. In fact, it's going to get reflected in the same surface. So we will have theta 2 and the theta 1, and this theta 2 will be coming back into the surface. Now this happens when there is critical angle. Okay. So if it's greater than the critical angle, it is going to reflect back to the same medium. Now at angles greater than theta c, what happens is the rays will reflect back to the denser medium. This is what is total internal reflection. So don't write down this short form TIR, always write down the entire form, total internal reflection. Okay, so that's important. Okay. So this total internal reflection will obey laws of refraction. If I get back to this previous one, if you look into the second ray diagram, you see that it gets reflected back into the same medium. Okay, so that means it has to follow the laws of reflection. Okay, and in simple words, already explained that theta c will be nothing but the critical angle, and we can easily find it out, right? So theta 2 would be 90 degree here. So sine of theta c is mu2 by mu1. So what can I ask you here? Maybe a numerical problem. Find out the critical angle, okay, for the interface, okay, where we are actually having, let's say, water on one side, glass on the other side. So you can take any sample value. For example, glass has got a refractive index of 1.5, 1.4, depends on what kind of glass you are considering. If it's a glass which makes a prism, it might be even 1.6. You have flint glass and ground glass, okay, and water is 1.33, and you can take the ratio between these two, and then you can see what is your critical angle. Okay, so that's the This is the other way of understanding this, that if the second medium is rarer, obviously, is air, that means mu1 is 1. So mu1 is nothing but 1. Then I can simply write it down as this. So mu1 can be written as only mu, and mu2 would be air, so mu2 is equal to 1. I can simply write down sine of theta c is equal to 1 divided by 2. That's it. Okay. So you can also find out the critical angle this way if you know that the second medium is actually air. Okay, it all depends on what's your aim. Okay, that's important. Okay, now let's just proceed further and try to understand critical angle of propagation. Now this is a descriptive part of this unit. Okay, where we talk about the relation for numerical aperture. So there is a term which is called numerical aperture. Okay, and what happens is when the light will enter the core, okay, of the optical fiber, okay, you have to know its effectiveness, within what range will this be actually suffering total internal reflection. Numerical aperture also helps me to actually create this waveguide easily, okay, and that's why we do it. So what happens is the light will enter from one end of the fiber, okay, one end of the fiber, and this is basically called the launching end. So you know the light is launched, okay, and the refractive index changes from core to cladding. This is something which you already know. Core is there is the cladding. Cladding will have lesser refractive index, core will have more refractive index, okay. But then let's imagine that there are two rays which will enter the fiber at two different angles of incidence. Okay, so I'll just make this show this diagram to you, and it will be a bit more clear to you. And it will basically make a cone kind of structure. Okay, so what happens is this is the ray of light that enters into the core. Okay, and you know this is basically the core which has got a refractive index of n1. Okay, but then on the other hand, if we are just looking into the cladding, this has got a refractive index of n2. So it's not that the cladding will have a lot of space. Main part would be the core, okay, and the cladding will cover it with a greater refractive index. So there is certain range within which the total internal reflection will happen. That is basically nothing but also a part of the acceptance codes. Okay. So before we proceed further, we'll just understand this diagram first. So we have this ray of light which is actually incident at an angle of theta naught. Okay. And then after it enters, it is entering from air to the, let's say, the core. The core will have greater refractive index. Okay, so that means it's going from a rarer to a denser medium. Okay, and based on this, it will actually behave, and it will give you the angle of reflection as theta 2. So this is one interface that we are basically talking about here. Okay, or theta 1, sorry. And the other part would be nothing but if this is theta 1, at this particular angle also, it will be incident at an angle theta 1, right? Because you know this line and this line are parallel to each other. This is a transversal, so these angles will be more or less equal. Okay. So what happens usually is that if the ray of light is incident at an angle theta 1, okay, and it is incident at such an angle that this ray of light will pass along the surface, that means this theta 1 would be nothing but the critical angle. So this would be nothing but the critical angle that we are talking about. Okay, so which is the critical angle here? 90 minus theta 1, because at this interface, okay, if this at this interface we have got the normal, okay, and we have got theta 1 here, so this is theta 1, so this angle would be 90 minus theta 1. So this 90 minus theta 1 will decide whether the ray will actually go away from the normal, whether it will go along the surface, or it will totally get reflected back. So if 90 minus theta 1 decides this, 90 cannot be changed, theta 1 can be changed. So that means if we can adjust this value of theta 1, we can actually adjust 90 minus theta 1 to counter the critical angle. Very important. Okay. So this is how you draw the diagram. So if I am asking you about numerical aperture, please draw this diagram clearly. Okay. And then once you have drawn this, you can go for the derivation part. Okay. But before that, definitely you have to write down a lot of sentences, but I already have explained it. So it should not be very much difficult. So as I say, we have got a ray AO. Okay. So if you are basically having this core, okay, the diagram might not be very good, but let's just imagine I'm drawing it here. Okay. This is the core, the top one is the cladding. We have got a ray AO. Okay, so this will be the ray AO incident at an angle of incidence theta 1. So I can draw a angle here. So this is theta 1. Okay, only the previous diagram is there in the code, and falls at an angle 90 minus theta 1 at B. If we just go into the previous slide, we know that it will actually fall at this particular angle, and this is 90 minus theta 1. Okay, let's rub this, looks too bad. Okay, so this is the core cladding surface. So this 90 minus theta 1 will actually represent the critical angle. Okay, so the critical angle is nothing but the ray is refracted at 90 degree to the surface normal. So if this 90 minus theta 1 is basically critical angle, that means the ray won't actually reflect back. It won't also go to the other surface suffering reflection. It will come back within the system. It will move along the surface, sorry. So this will move 90 degree to the surface of the material. Okay. So you have to understand this. When theta naught is less, 90 minus theta 1 will be greater than the critical angle. How? If you just look into this particular diagram, if theta naught is less, okay, this will be more or less. Okay, if this is less, this will actually affect, this will be less. If this is less, this will be more, because this is 90 minus that value. Okay, so let's say if this is, let's say 20 degree, and let's say this is, let's say around, this will be also less. Okay, so it may be, let's say around 15 degree. So if this is also 15 degree, this will be 90 minus 15, which is 75 degrees. So this may be the critical angle. But if this is more, let's say this is 25, this will be 20, and this will be again 20, and this will be 90 minus 20, so this will be 70. So this will be, if 75 is the critical angle, this is less than theta c. This is quite logical, okay? And that's why we say that if this theta naught is changing, the critical angle we can easily adjust, okay? And if you just look into this, that means that if theta naught is less, we are going to have the angle of incidence at the core cladding surface greater than the critical angle. And if it is greater than the critical angle, this will undergo total internal reflection. Now this is something which you have to understand. Okay, this theta naught, that means the angle of incidence, will decide whether the ray of light can actually travel inside the waveguide. Okay, if theta naught can decide that, that means this will actually be defined as the waveguide acceptance angle. Waveguide acceptance angle. Okay, so you understand what is acceptance angle now. Okay, now what is sine theta naught? If you take the sine of this accepted angle, this is called the numerical aperture of the fiber. So you see, this numerical aperture is a very tricky term. You have to understand certain things before you explain this. Okay, so this is called the numerical aperture. You have the waveguide acceptance angle, take the sine of that, that is the numerical aperture of the fiber. And what does it represent? It represents the light gathering capacity of the optical fiber. And I think this is logical because, you know, how much light can an optical fiber accept, or how much electromagnetic waves can an optical fiber accept will depend on a certain range. Okay, if this acceptance angle is more, it can accept the light for a larger range. Okay, so that means we have to direct the light at a certain angle so that we can have the entire signal transferred from one side of the optical fiber to the other side of the optical fiber. It goes beyond that, we'll lose signal. If it comes less than that, we'll lose signal. Okay, so we have to do that optimization. That's very important. So this is there, but then there is a small derivation here. So you see, the explanation is very much logical. You have to use the laws that we have. Okay, and based on this, you can actually explain this and write down the numerical aperture. So what we see here are, there are three refractive indices involved. The first is the surface or the medium from which the light is getting incident. The second refractive index will be nothing but that of the core, and the third refractive index will be that of the cladding. Okay, so it's the surrounding medium core of the fiber and the cladding respectively. Okay, so there are 2 points at which refraction happens. One will be at point O, which is nothing but separating N0 and N1. That means the surrounding medium and the core of the fiber. And here we can actually apply Snell's law. So what is Snell's law? The refractive index of the first medium into the side of the angle of incidence at the interface between the first medium and the normal is equal to the refractive index of the second medium and the angle of refraction at the second interface and the normal, right? That is the definition. So we'll accordingly just separate it out, okay, and just put the values. Don't get confused here. This is n0 sin theta naught is equal to n1 sin theta 1 because we are talking about the refraction happening at the air, let's say, and the core interface. So if you just want to find out sin theta naught, you can just simply write it down as n1 divided by n naught into root over of 1 minus cos square theta 1. Sin square theta 1 plus sin cos square theta 1 is equal to 1. So that means sin of theta 1 can be written as root over 1 minus cos square theta 1. So this is my first relation. Okay, I'm just writing it down in terms of cos and we'll see it how and why. Okay, and next what we have at point B. We have got point B, that means the core cladding interface. Now in the core cladding interface, the angle of incidence is 90 minus theta 1. We have seen it in the diagram, and the refractive index was n1. And the second medium, that is the cladding, we have got n2. And let's say this is the critical angle, so this will be sine of 90. So if 90 minus theta 1 is the critical angle, the second angle has to be 90. If it is greater than the critical angle, then only total internal reflection will happen. But we have to look into the boundary conditions first. So if that is 90 minus theta 1, we have got n2 sine of 90. So if I just take this sine of 90 minus theta 1 is cos theta, we already know it. And that's why the previous relation also we have written in terms of cos. The sine of 90 minus theta is cos of theta 1. It can be written as n2 divided by n1. So you can substitute this value, which is in cos, in the previous equation, where we got sine theta naught is n1 by n0 root over of 1 minus cos square theta. Cos theta is n2 by n1, so I can just simply write it down as n2 by n1. So look into the beauty of this. Okay, it becomes more simplified. So this side of theta 1, which is nothing but the numerical aperture, will be root over of n1 square minus n2 square divided by n0. Okay, therefore numerical aperture sine of theta naught is equal to root over of n1 square minus n2 square divided by n0. That's the definition of numerical aperture, and that's the relation that we usually use to find out the numerical aperture. Now things becomes very easy. Okay, we should know from what medium it is getting incident. So that means, let's say air. Okay, and then secondly, on what is the refractive index of the core. Okay, and then we will see what is the refractive index of the cladding. So if then based on this you can find out what is numerical aperture. Let's say air is n0, so this will become 1. Let's say n1 square, which is the core, maybe 1.465. If you remember, you have got doping with germanium. Okay, we have that, and then we have got n2, which should be nothing but 1.45. let's say you put the values, you can get the typical numerical aperture value. Okay, that's it. So if the surrounding medium is here, as I said, and not is 1, so you can just take this. So you want to have an optical fiber and you want to have a signal getting into the optical fiber, let's say underground, let's say in water. Okay, then you have to consider this as 1.33. It's not always here, depends on where the designs are made. It's very important. Okay, so I do have some questions for you. Okay, and this is the question that I'll be giving it to you. Okay,